Um, Hello everyone, and this is Jiancheng Yang. I'm from Shanghai Jiao Tong University, and I'm also a visiting research fellow at Harvard University. And today the talk will be about clinical AI and medical classification Dexlon, which is a recent article and a data set released by us. And before the presentation, I will give a self-introduction. And I did my bachelor degree and master degree in Shanghai Jiao Tong University, and I'm doing PhD now. And I have been in France for 2 years with a double master degree, and now I'm visiting Harvard Visual Computing Group. And my primary focus, research focus, is medical image analysis, 3D computer vision, and trustworthy machine learning. And in medical image analysis, I collaborate with several clinicians to work on clinical science, especially lung cancer and thoracic diseases. And I also work on methodology research, primarily on the 3D computer vision and geometry, and also something in trustworthy machine learning. And I also develop data and benchmark. And today it will be about the data and benchmark actually. And my research has been published on top journal and conference, such as Cancer Research eBiomedicine, CVPR Mikai, and NEUROPS. And I'm also the leading organizer for the Refract Challenge, which is an official Mikai 2019 challenge. Okay, today the talk will be about the clinical artificial intelligence. So I will talk about the clinical AI first, and then I will talk something about the MedMNIST, which is very suitable for the beginners and also the researchers. And I was told some audience are interested on how to developing the research data. So there will be a slides about how to develop a research data. Okay, so I will first talk something about the clinical AI. And the clinical AI is a very big terminology. So I will introduce um, uh, the clinical AI in three aspects. Actually, this is my opinion. So it is a very big landscape. Okay, so first I will talk something about the use case of clinical AI. So um, basically, there are many things that clinical AI can help the clinicians and the patients. So it can be used for the diagnosis, such as when people doing the radiology test and histopathological test, and the AI can help the doctors to rate the image, and it can help the clinical intervention, such as it can help the doctor to select the best therapy for the patients, and it can also help the follow-up. For example, for a lung cancer patient, he need to go back to the hospital maybe every month or every 3 months. So the AI can help the doctor to manage the non-nodule or help the diagnose. And AI can also help in the clinical prognosis. So the prognosis is about predicting the future, such as predicting whether the patient will survive or not. So it is something that AI very suitable to use. And it can also working on visualization, such as 3D reconstruction of the lung. So here, this is a 3D reconstruction of a lung, and it can be really critical for the thoracic surgery because it can be both important for the patients and the clinicians. It is better do the surgery planning. And it can also work on the drug discovery. The drug discovery, for some people, it is not clinical. It is about fundamental biology, but I just put it here as the drug discovery, AI for drug discovery is very, very important topic now. And recently there is important paper that, it's not a paper so far, it's AlphaFold 2, and the AlphaFold 1 is something that changed the rule. So it is also something very interesting. It is about the protein folding and protein interaction. So it is also an interesting and important topic. And for the machine learning people, maybe we are not very interested in the use case, but we have to know about the data modality and the algorithm task. So for the clinical AI, there are many data that involve, such as medical images. This is the primary focus today. There are so many kind of medical images, such as the CT scans, the computed tomography, and MRI and PET, and also many geometric data. For example, the protein, the structure, data structure of the protein is a geometric data. And there will be also many medical texts, such as the medical record or other stuff. And there will be also the graph and geometric data. The graph, sometimes it can be the knowledge graph, the medical knowledge graph, and the geometric data. It can be sometimes while processing the shape, and also something like the protein structure. And for the machine learning people, we are interested what kind of algorithm task that the clinical AI generally involve. For medical images, there will be medical classification, such as the diagnosis from the CT scans. It is medical classification or detection or segmentation. Reconstruction problem, it is also possible to use the generated model to in the medical images, such as the super resolution or denoising the images. And there will be also the imaging captioning. There is some task like medical imaging captioning. Although I don't think this is a very good solution, but there is also this kind of task. Given image and output the diagnosis suggestion or somehow other stuff. So it will also be image captioning. And for the medical text, there will be medical task classification or medical question answering, such as the very famous IBM Watson. This is a intelligent agent about the medical question answering. And for the medical text, if we want to build knowledge graph, the named entity recognition is also important task. And we're also interested on the geometric modeling in image or something in the geometric data. Okay, so I just gave a landscape of clinical AI in my site. So hope it help for understanding the clinical AI. And when I do the research for the clinical AI, I think there is primarily two directions for the research of clinical AI, which is upward and downwards clinical AI. So what does this mean? So we know there is two directions for modern medicine, which is precision medicine and also the stratified healthcare. So the precision medicine is to propose a personalized healthcare for each individual, and the stratified healthcare is something to make the healthcare system more suitable and robust for every individual. And so there is also this kind of two direction of the clinical AI. So for the downwards clinical AI, that means there are many tasks that the patient, the clinical, the clinicians can do very well, such as lesion screening, lesion detection, and organ and tumor segmentation, and radiological diagnosis and treatment suggestion. So this kind of task is the clinicians can do very well, and they are trained when they have education, so they're trained to do this kind of task. But if we can build large data sets and we can build a data set for the top hospital and with top clinicians, we can make this ability into the AI agent. So we can empower the junior clinicians and also reduce the duplicated effort for the clinicians. So it is something about the downwards clinical AI and can be helpful for the stratified healthcare. And for the upward side, and it means there are many clinicians, many kind of tasks that the clinicians cannot do it very well, such as the cross-model radio cross-model prediction from the radiology image to the pathological diagnosis, or even do the genotype diagnosis, or even we can predict the future and predict whether the patient survive or not. So how can AI can do this? It means we can collect the data. We can collect the data with the with some information we want to use, and we can also retrospectively connect the annotation from some other cross-model information. For example, we can connect both the micro information and the macro information. So, and we can build a machine learning model to predict the future or predict the micro information from the macro information. So this is something that AI can do, and in this way we can let the clinicians see the invisible and facilitate the the personalized healthcare. And I think this is two direction of the clinical AI, and there is also a very famous term about the clinical AI that AI will not replace the doctors, but the doctors who are better able to utilize the AI will replace doctors who cannot. So this is some terms that really good summarize the AI today. Yeah, and this is some introduction about the clinical AI, and later I will talk something about the data. As we know, so far the deep learning research is driven by the data sets. We know some very famous data sets such as MedMNIST or a medical there's Shakespeare and Luna, and for protein analysis there is PDB or many kind of data. And we know the deep learning research is driven by data set. So later we will talk something about our recent article here. It is about MedMNIST classification Daxlon. And this paper is recently accepted by ESP 2091. And it will be presented in the conference in April or later. I didn't believe the time. Okay, so I will talk something about the paper. This paper is printed by this author Jiancheng Yang, Rui Shi, and Bingbing Ni. And for the medical image analysis, there is a lot of difficulty for the beginners and even for many machine learning researchers, such as there are massive data formats such as DICOM, NNI, NRD, and so on. So they are really massive data formats, and there is massive data modalities such as X-ray, CT, MI, OCT, and so on. And for the beginners, there are many type of license and user agreement. And also about the data, there is many kind of resolution and 2D or 3D. And it can be non-standard pre-processed, and it can be various in data size and data scales. So I think the medical image analysis is not very friendly for the beginners and even for many computer vision and machine learning researchers. So we want to build something that is very friendly for the users, which can be educational and standardized, diverse, and lightweight for the users. And here we give an overview of this data set. So there was 10 subset of MedMNIST, which is come from the many open source data, and we have pre-processed the data into a very standard format, which is 28 by 28 images with standard labels. They are the classification labels, and all the data is open source, and you can just use this with one line of code. Yeah, it is very easy to use, and you can also directly download the data from our website. And then I will introduce the data. The MedMNIST is very diverse in data modality and task and data scale. The data modality cover the primary data modality in medical image analysis, such as pathological images, X-ray images, and the dermatoscope image, and OCT, and fundus camera, and ultrasound, and also 3D images. But we have processed the data into 2D, and which is CT scans. And the task in the MedMNIST is also very diverse, which can be the multi-class classification, binary class classification, and multi-label classification, and also the ordinal regression. And the data scale in MedMNIST is also diverse, which it is from 100 and to 100,000. So it can be used for many cases, and we believe it is very suitable to benchmark the AutoML algorithm and also many kind of multimodal machine learning algorithms. So I will just give a very quick review for each data. So the PathMNIST is about the pathological images. The pathological images is a primary medical way to diagnose the cancer. So it is about it is a multi-class classification data, and also the chicks X-ray with 14 diseases, and also the dermatoscope for the skin lesions, and OCT for the retina diseases, and chicks X-ray for the pediatric chicks X-ray images, and then the retina MList for the fundus camera, and for 5 level of the DR, and then the ultrasound, which is a binary classification for breast, and then of the mentioned data are 2D images, and we have also processed something for the 3D images, but we have pre-processed the data into 2D. So how can we do this? So this is the 3D scans, and we process the data into in three views, which is axial, coronal, and sagittal view. So and we use a CT scan and 11 type of body organs. So we process the 3D scans into 2D in the three view. So it is a organ MNIST in three view. And they are also different in the data scale. And so the MedMNIST is very suitable for many cases, such as for the educational purpose, and also for the researchers. We believe it is good to benchmark the AutoML algorithms. And here we introduce many AutoML tools, such as AutoKeras, and AutoSKlearn, and also a commercial tool, which is Google Cloud AutoML Vision. And to compare with the AutoML tool, we also introduced a very standard ResNet with early stop strategy on the validation set, and we tested on the test set. And in case of maybe some audience do not know the AutoML is we want a single algorithm and a single maybe a script, a predefined script, but we do not need to manually tune any hyperparameter, and we just feed the data to the algorithms, and we can get the model. So it is about AutoML tool. And we do the experiment on all the data set, and we find the ResNet here, and AutoSKlearn, AutoKeras, and Google AutoML Vision. And the result is very interesting. First, we find the commercial tool work pretty well. So it is a winner in many cases. And we consider two metrics, which is the AUC and the accuracy for each data. So the AUC is a threshold-free metric, and the accuracy is we need a threshold, which is the 0.5 to determine the accuracy. And we find the commercial tool work pretty well for many cases, but it is not always be the winner. You can find in some cases the commercial tool does not work work well, and even the very standard ResNet can be the winner in some cases. For example, the organ MNIST, you can find the ResNet, very standard early stop ResNet can be the winner as well. So in this case, we find so far the AutoML tool, at least for these three tools, they do not work as we expected, even though the commercial tool, we need to spend some money on this. So it is very interesting to develop AutoML algorithms based on the MedMNIST data set. And it is a finger about the for different subset, and we find for many tool there is a very serve overfitting issue observed on the image from the data. For example, for the OCT images, it is very high training accuracy, training metric, but it relatively low test accuracy. So actually, we are also working on some algorithms on the AutoML algorithms on the MedMNIST data. So as a summary, so the MedMNIST can be educational, and we have open source all the subset with the CC license, and it is very easy to use for educational purpose. And we are very happy to hear that the data has already been used for some high school and also some university course. And the data is standardized, and the data is pre-processed into the same format. And so it requires no background knowledge for the users. And it is very diverse. So the MedModel data set cover the diverse data scale, which is from the 100 to 100,000, and also diverse task, which is binary or multi-class classification, and ordinal regression, and multi-label classification. And the MedMNIST is it is designed to be very lightweight, which is 28 by 28. So the data can be even run a CPU. So if you want to rapid prototype your algorithms and experiment the multimodal machine learning or AutoML algorithms, you can just use the MedMNIST data. Okay, so this is a quick introduction to the MedMNIST, and the data is pre-processed pretty well, so it can be just used with one line of code. You can just call the data, and you can get a standard PyTorch data set. Then you can just print the information like this stuff. So again, how many data are involved in a data set, and where the localization and the split and the task and channel, and what does the label means, and the number of samples, and description, and also the license. So so we believe the MedMNIST is designed to be easy to use. And if you have any suggestions, just feel free to contact me. And then finally, we will talk something about developing research data. So for the MedMNIST, it is open source data, and maybe some people want to know how to develop their own data set, especially for the research purpose, how to make the open source data set. So there is primarily 5 steps. The first one is we need to find an important research question. So this is something I believe the most important things for the research. So there has already been so many kind of research data. So you need to define important research questions, and then you need to collect the data. Maybe the data can be public data. For example, the ImageNet. Most data in the ImageNet is from the website, is from the web. So the data can be public, or it can also be private data for maybe your in-house data. But if the data is your in-house data, you need to consider the privacy when you want to open source the data. And then you need to make the annotation for the data if you want to develop a supervised learning data set. The annotation can be by any human and or by the expert if it is a medical data. And sometimes you can use some machine learning tools or some computer vision tools to help the annotators to make the annotation. And here, sometimes it is a human in the loop annotation procedure. And then you need to make the quality control. So this is a very important step, although maybe in the paper, this is not many things to be mentioned, but this is a very important step, and it is spend a lot of time for the quality control. You need to make the annotators check the data and also check the annotations. And maybe you can develop some models based on the data and do the quality control. And then finally, you need to do the benchmarking and the evaluation. So you need to design the metric and also design the baseline for the data set. And then after finish this, you can just consider how do you open source the data. So where to host your open source data. So what kind of license you will use. And I have another talk about this topic. So you can just check maybe on my personal page, but this talk is in Chinese, but the slides is in English. So you can just check this talk. And just, by the way, I will just introduce another data very briefly of ours, which is the refract data set and the refract challenge. So the refract data set is about how we can develop a deep learning agent to automatically detect and segment the rib fractures from the CT scans. So this study is published on the eBiomedicine recently, and the data set is open source, and we have a release around 616 CT scans on the website. And we also host a refract challenge, which is the official MICAI 2019 challenge. And you can still use the data. So the data is, the website is now an online benchmark and using the website. The refract challenge is the first large-scale benchmark for automatic diagnosis of refractures, and it can, for the machine learning people, it can serve as 3D detection, segmentation, and also classification. And there are more than 400 people to be the participants, and now as it is an online benchmark, so there will be more participants now. And this is our organization team, and we are from Shanghai Jiao Tong University, and also the Huadong Hospital from the Fudan University in China, and also from DNA Technology and Harvard University. Okay, so this is primarily about the research, and finally I will talk something about my research. So maybe some audience can just contact with me and do the potential research collaboration. And my research is primarily on the medical image analysis and also 3D computer vision and trustworthy machine learning. And medical image analysis, I primarily work on lung cancer and thoracic diseases. We have a series of study on this topic. And we also develop a specific methodology such as 3D medical imaging data, such as 2D to 3D transfer learning, the pre-training, and also how to develop a method for the anisotropic volume, and also the time series problem and the probabilistic machine learning. And we also developed some methodology about how to process the 3D geometric data, such as 3D point clouds or the 3D pose and so on. And I have some expertise on the 3D computer vision and geometric modeling. And for the trustworthy machine learning, and we have study on the adversarial security, and also we are working on the model verification and domain generalization and federated machine learning. And if you are interested, you can just contact with me with the following area of the research, especially on the large scale medical image analysis. I have experience in 3D images and shape and geometric modeling, and also the translational research, such as lung cancer and thoracic diseases or other important diseases. And recently, I'm very interested in how to process the EM image and the protein analysis, such as the protein folding and protein-protein interaction. So if you have the clinical background or biological background or the computer vision, machine learning background, maybe you can just email me with to do the potential research collaboration. Okay, thanks for listening, and this is a talk, and you may find all the materials on my personal homepage. Okay, thank you.